Welcome to a video write-up of the readme pwnable challenge from the 32C3CTF. Just as a full disclosure, I didn't solve the challenge myself during the CTF, but I spent a lot of time on it, and in the end I worked through write-ups from other people, and now I researched a lot, and now I really fully understand this, how it worked, and understand so much more about how a binary is loaded into memory and how everything looks like. So that was a very cool experience for me. And so now I want to give you this kind of different write-up, not in written form, but in video. So maybe that helps somebody else to also see how you can, how to use certain tools to achieve those things. So let's get started. First thing I do is I copy the link so I can download it later. And what I use for debugging is Vagrant. Vagrant is a virtual VM wrapper around VirtualBox. So there's a Vagrant file that specifies how the virtual machine should look like, and a Vagrant setup that sets up it with tools and everything. My VM is based on a VM that is from GitHub. I have the address here, but I extended it or changed a little bit around it. So now I'm just starting up the VM, and then I can connect to it with Vagrant SSH, especially because I use Mac. So it's very important for me to have easy accessible VMs, especially with Linux stuff available. There's also this shared folder, which is automatically shared between the Mac and the VM. So whatever is put into the shared folder, I can access on both. And now I use wget to download the link that I earlier copied and unpack it, and yeah, that's the README file. And first thing I obviously do is I do file on the README to see that it's an ELF 64-bit Ubuntu, what am I saying? Linux executable. And again, as I said, this is not a live recording of me solving it for the first time. I knew the solution and I recorded myself and now give commentary to it. Well, here I did strings on the binary to have a first look, and I found this 32C3 fake flag in there, which obviously looks interesting. So we probably have to get the flag from the real binary. So then I decide to open it in IDA, but I'm stupid because I actually have a real IDA license, but only IDA standard, and IDA standard doesn't support 64-bit. Fail. So then I use Hopper, which is a great, fairly low-cost disassembler, which is actually worth buying. And I immediately look for the strings because, those give us the points in the application where interesting stuff is happening. And there's this fake flag, which is in the data which you can find in the data section. And the other strings are near the code stuff in the read-only data area. So the flag is in the data section because that's also writable. And those strings are in the read-only data section. Well, and then I realized maybe I should quickly try out how actually the service has to be interacted with, and it asks you for a name and it will print the name, and then it asks you to overwrite the flag. And it's always a good idea to just maybe throw a lot of characters at it and see if something interesting happens, but well, yeah, doesn't look like anything is happening there. Then I opened binaryninja because I recently got beta access, and I thought, let's check it out, let's see how it's looking. But then I got confused because it didn't show me the function that Hopper was able to find. And for a second I was a little bit startled what to do next. And that's why it's good to never trust one tool, and why it's good to use different tools, because some tools will fail, other tools will work or will be more convenient. So in this case, for example, I use Hopper to find the address, and then I can jump to this address in binaryninja. But it didn't recognize it as a function, but I think it was Command P. Basically, in IDA or Hopper, I can specify that I want this data here interpreted as a procedure. And so now it also created a call graph for it. And here's the initial hello string, and you can also see the printf that is following right below it. And then there's a gets call, and gets is a very awful function. You should check the man page. There's this funny bugs section here that says never use gets, because it's just awful, and that is clearly the vulnerability that we have in our program, which means we can basically overwrite the whole stack. And then it prints the nice to meet you with the %s, and then I realized, oh, it showed back the whatever we type in. I should have also checked, obviously, if there's a format string. So just here show again that there's no format string vulnerability, obviously, here, but that's maybe a good thing that you should usually do, check if there's format string exploit. Well, yeah, and then now I start to have a little bit look at the call graph, and we follow like the arrows and where it proceeds, and after the gets, it will go to a get character, and then it will check if that character was a new line, basically if you hit enter. If you didn't hit enter, so if you entered any other character, and then this byte, the value of the current character, will be moved at this address, and that is the address of the flag. So that is after the overwrite the flag string that gets printed. So we are literally like the characters that we then enter are then written at the location of the flag. And RBX is like the offset, like which character we are overwriting next. And with every character that we write, it gets incremented by 1. And it will then compare to hex 20, which is 32, and then it will branch either way. So it will either loop back up, or will like exit and print the thank you message. So RBX, or in that register, there's a counter how many characters we have already overwritten. So, but if we hit enter, we will land in this left branch where it will set up the parameters for a memset call. With x or esi to 0, and edx is calculated from subtracting ebx, and ebx was the amount of numbers we have already written, and edx was set to hex 20 there at the start, means that the length, which is Hopper nicely showing the parameters, the edx is the length parameter, is now basically the difference, like the remaining characters that we haven't overwritten yet, and the memset will set it to 0. So it looks pretty solid. It will clearly overwrite the flag at that position. And you also notice here that RIX is like loaded from this other FS register, and then it gets moved on onto the stack. And that is a stack canary. So FS contains a random value, and that in the beginning of the function, it gets moved onto the stack. And if we like smash the stack and overwrite this random value, it will be read at the end again from the stack and compared to the original value in the FS register. And if that XOR doesn't produce a 0, so it means that it was equal, we will either return, or we will jump to a stack check fail. Yeah, and then I open it in GDB, and I think about where I break, and there is no main function, so I decide to break before the gets, because that will show us the state of the stack before we overwrite anything. And the second breakpoint I will set is right before we decide if the stack canary was smashed or not. So we can then have like a breakpoint at a state before we have the overflow and after we have the overflow. So now we start, and that looks super pretty. This is an GDB extension called pwnDebugger, pwnDBG, and it's pretty cool. Like the colors are indicating in what section it is. For example, red addresses refer to code sections. So that's pretty useful. And it also shows you, for example, the parameters of the gets call and stuff. So it's very useful. Yeah, now I'm just like playing around, putting some input in. And here, for example, we hit the breakpoint at the stack canary check, and error X has the value that is was read from the stack, and now it's compared to the FS register, and yeah, that's the random value, which is interesting that it always has 0 in it, because it's interesting that it has 0 in it because if imagine you would be able to guess the stack canary, you could do a successful overflow, like if you leak the canary somehow. But the issue will be that often overflows are string related, and strings end at 0 at a null byte. So even if you have a successful exploit and you know the stack canary, maybe this forced 0 byte in the stack canary will stop you from actually exploiting it, because you cannot set a 0 byte in the middle of a string. So that's just a very clever way how they designed the stack canary. Yeah, now I return, and maybe remember like the address where we return to after the program, because we will now look on the stack and we will see this return address on the stack. And because we started again, the stack canary here has now obviously different values, but again with the 0 byte, in case we have like a string copy based buffer overflow, even though we maybe know the random value, we would be stopped there because we cannot insert the 0 byte. And again, the return value here, the 6E7, is like 2 below the stack canary there. So that is the address that this function returns to. So if we could overwrite that, we could obviously redirect code execution somewhere else, but the stack canary is preventing us from doing that. Because if we enter like a lot of characters and we have a look at the stack, everything is overwritten. But you can also see that now the RIX register that earlier like read the stack canary from the stack was also written with A's now. So yeah, obviously that is not a valid stack canary, and we will follow into the stack check fail function instead of returning. So even though we have overwritten the instruction pointer now, we will, instead of return, we will now execute stack check fail, which will then exit. And yeah, notice how this caused now a segmentation fault here. And so the reason a binary can crash can be many reasons. In this case, it was a segmentation fault, and if you look at like the code where it crashed, there in the code output, it was in the get environment functions. So it had something to do with the environment variables why it crashed, and it tried to load a value and like try to access 414141, which was not a valid address. So now let's have a little bit of a look at the flag and see like flag gets overwritten, and you can clearly see that yeah, it gets overwritten with whatever we enter. We can also set a breakpoint at the address where this single character overwrites a flag character, and then we can always continue and inspect the flag to see how it slowly gets overwritten with the characters that we have input earlier. Yeah, and you can see that the flag address always gets overwritten. Maybe interesting to try is what happens with an empty string, and then it's all zeros, because the memset will then set 32 characters to 0. So yeah, it looks solid. There seems to be no way around it. But if we search for 32C3 in memory, weirdly, we find another occurrence of this flag, even though we have overwritten it. And if we restart it and search, we obviously find both locations. And that's very interesting, and I didn't know about this before, but it makes sense. you can check this through the proc pseudo file system. So what I'm doing now is I get the process ID of the current process, and then I access the proc memory map entry for that process, and it shows us where memory is mapped to, and this tells us that the binary is actually mapped at 2 different locations. One time it's mapped as read write, and the other time it's mapped as read and execute. So our code had always like the addresses of the code started with 40. So this is where the binary is mapped as executable, but the address where we write to, basically the flag, is at 60, so that is in the writable segment. So now I'm playing around a little bit more with the crashes. So that many characters cause the segmentation fault, and I kind of try now to cause a kind of different conditions, because as I said, the binary might crash out of different reasons. For example, the segfault now is likely a different reason than the segfault before. That's because, for example, if we write all the way to the bottom of the stack and then try to write further, we try to write in memory that doesn't exist, and then this will cause a segfault because it's unmapped memory. But that is then a different reason for the segfault than what we had earlier, where it segfaulted it in the get environment call because it probably tried to follow certain addresses on the stack which we have overwritten with A's, which again is non-mapped memory. But those are different reasons why it crashes. So yeah, you see on this stack there are a lot of those 7 FFFF addresses, and those are pointers to other values on the stack. Yeah, so if we overwrite one of these, then that's the reason why the get environment call crashed. So now I'm just getting like the amount of A's I need to like fill basically the stack. And again, this will smash everything, all the pointers on the stack. And if we now continue, we will see that we again get a segfault. Yeah, and the segfault again is in get environment right now. If you even look closely, you see that it also has to do with the stack check fail. So somehow stack check failed, wanted to look up get environment variables, and if you look very closely, right at the top you see something with libc fatal std arrow. So maybe the stack check fail tried to get the environment variable libc standard arrow thing, which gets important soon, but keep that in mind. So those pointers here on the stack are actually pointers to strings, and they are the program arguments and the environment variables. Now I started the program with 4 arguments, so now the array has 5 elements, and those are all pointers to strings and are pointing to the program arguments that were supplied. And the first one is obviously pointing to the program name. Like the first argument is always the name of the program. And with info variables argv, we can also find this libc variable that contains this this address. And if we interpret this as a string, like the first address there as a string, we will see it's a program name. Now let's make a little bit shorter overflow, and now we get the stack smashing detected. So this is actually what's printed from the stack canary fail, and you can see that it prints the program name. And now you can guess where it takes the program name from. And if you go one element further of the argv array, you obviously can access the other arguments of the program. Okay, so basically I do the same input now in GDB as well, and then I want to change the argument, the first argument pointer, so basically changing the name of the program. And I do this by just simply setting the first address to the address like of the second argument. So then instead of pointing to the real program name, it's then pointing to AAAA. And you can do this with set. Okay, now we can verify that the first array entry actually changed, and it's instead of pointing to the program name, it's now pointing to AAA. And when we now continue and get this sig abort, the stack smash fail, you see that instead of printing the program name, it prints AAA. So maybe it clicks now, and maybe you have now the idea how maybe this challenge can be exploited. So let's have a look again on the stack, like where this pointer was. We want obviously to overwrite this pointer with the address of the flag, because then we can leak the flag through this arrow, right? Makes sense, right? So with Python, we can then calculate this offset, how much we have to fill and overwrite, and then we can like write the address of the flag in the correct position. So I tested here and I realized I'm short by 8 characters, and I didn't overwrite the program name yet. And I realized I used the wrong address, so I have to obviously calculate the offset from 0.8, and then the next 8 bytes will be the pointer to the first argument. And if we run this now, we can inspect the stack and we can see that now we have those B's and Z's there. And when we continue, we get a segmentation fault. And then when you look closely again, so that was actually a new different segfault in a different place. It segfaulted in strl then. So that's what I mean. Like, a crash is not just a crash. You know, this program can crash in so many different places, and only one particular crash place is interesting and important to us, which is this proper sig abort with a stack smash detection, so we can leak the flag. Now I decide to convert this to a script, because I want to use structs to properly convert the address into a string. So yeah, we can build a nice exploit. So at this position now, I use struct to convert the address. So now I search again for the 32C3 flag to get the address of it, so I can set the proper address for the argument. So now I'm getting eager to try that out. But first fail is I stored it in the wrong folder. And I was so eager to try it that I failed to realize that I made a mistake. Yeah, looks about right, seems to work. I use the arrow redirection to get the input to GDB, but it didn't work. We didn't get the desired output. Well, I was stupid. I forgot the new line. Obviously, we basically have to hit enter. So, and then we also have to overwrite the flag with a value. But I guess now will it work? Fail again. What did I do wrong now? Looks correct, but again, forgot the second new line. Now we run it, we continue. We check out the first argument, which was successfully overwritten, and we can dereference the pointer and interpret it as a string to see that it's now pointing to the flag. And if we continue, we get the successful sig abort and the stack smashing detected message with the flag. That is pretty cool, huh? We test this with a regular program, also works, amazing. Now I guess sounds solved. Let's get the IP again from the challenge, throw it against it, but it doesn't work. Now we solved the first part of the challenge. We have a way how we can leak the flag from the process, but it doesn't work with yet with the remote challenge. To simulate this, I decided to install SoCat really quick, to show you what is basically happening. Never really used Socket, had to Google how to use it, but yeah. So Socket is running now, and basically I can connect now to a local port, and it will execute the readme binary, and I can interact with it like with the real challenge. So I can enter the stuff, and yeah, seems to work. Well, I put a loop around it so I don't have to start it by hand all the time, and I had a sleep one because I had some bad experience with scripts that were in an endless loop that went rogue and I couldn't like stop them anymore. Okay, let's use our proof of concept exploit and throw it against it. Well, it didn't appear through Netcat, but it did appear on the server side. That is where the second part of this challenge like starts. How can we leak this message over the network? Because this gets printed to the console and not to standard error or standard out for that matter. And like earlier I mentioned that there was a get environment crash on libc fatal standard error. And if you look that up, that is an environment variable that will redirect this error message onto standard error. And you can make the assumption that maybe the server will redirect the standard error output to you. And you can make like a small test. Here I have just like redirected the standard error to def null. So anything that gets printed to standard error would be removed. And when we execute it just regularly, it will still show the stack detect message. But if we use this environment variable, it will disappear because now it will be redirected to def null. So it shows that this environment variable is actually affecting where this the stack smashing detected message will be printed. So basically we have to somehow change the environment variables of our program. I mentioned earlier that they are also stored on the stack, and you can get the address from the environ variable. And this is like the program arguments. They are also on the stack. They also have this array here with all the different environment variables. So if you can like overwrite like one of those addresses, then with pointing with an address that is pointing to this new environment variable that you want to have, then yeah, this program like has this environment variable then. So basically we can do the same thing. We overwrite the first address of the environment pointer. First we have to like overflow 8 more characters, but the next 8 byte will be the address of the first entry of the environment array. And you can, very clever way what you can use here is the address of the flag that you overwrite, because that is a fixed memory location that you control. And instead of overwriting it with gibberish, you can overwrite it with the environment variable libc fatal standard error. You can verify that and see that now the environment is pointing to this variable that you now control. First, I realized I did another mistake. It somehow didn't work, and I realized I forgot again, screwed up the new line. Okay, now we can try it again. We can inspect the stack and the environment variable. Indeed, the environment variable now points to, or the first entry in the environment array points to the libc fatal standard error variable. So this looks like it works. So let's just throw it against the server, and yeah, there we have the address. We successfully exploited this, and we leaked the stack smashing detect error message over the network. Thank you very much for watching. This was a first attempt of creating like a video write-up of a CTF challenge that I very much enjoyed. I would be very happy to get like feedback, and not only on like the techniques that I used and what I could do better, but also like on the video format, because this is kind of an experiment, how to hopefully maybe make those more exciting for people to watch, and that it maybe looks more interesting or engaging. So if you have anything to say about it, I will be very happy to hear about it. Thank you very much.